So for our project, we decided to focus on the common evolutionary algorithm design problem called the knapsack problem. And the premise of this problem is that you have a bag with fixed dimensions, be that weight, volume, etc., and you can only fit however much in there, and you want to maximize the value of those items. And this seems like a very simple problem at first, one that could be simply assessed visually, or you put in the gold, which is worth the most. But as you add more and more parameters and bring it less away from a real world analog, clearly becomes much harder to solve and a perfect problem for this type of algorithm. The procedure for the knapsack problem is the same as any other genetic algorithm: initialization, mutation, and crossover, followed by selection. So for us, what that means is that we are going to initialize the parents by randomly selecting an item and filling the bag to its maximum capacity in order to avoid wasted generations early on in the procedure that would be operating on a non-full bag. And then once the knapsack is filled with all the items, we assess its fitness, and then we begin to mutate and cross over between other parents, and then again assess fitness, and then we select the best candidates and make children from them again, much like found in nature. So while we do this mutation and crossover, we have to ensure that our new children are going to fill the requirements of the bag, be that not exceeding the weight, volume, or max number of items. And once we've checked that, it will become a valuable candidate to become a parent for the next generation. We focused on three different crossover methods, the first being two-point crossover, where you randomly select 2 points within the string of genes, and you splice at those 2 points, and you simply combine two parents to form two different children. This method is very common in genetic algorithms and works quite well. Another method that we used was called partially matched crossover, which is also known as PMX. And in PMX, you swap the selected substrings just like in two-point crossover, but then when filling in the outsides, you simply use all the leftover genes from the first parent, and then anything that is not still matching, you index swap or fill out in order, whichever one you choose. Ordered crossover was the third form that we tried and is very similar to PMX, but the difference being that when you replace the substring, you then place the genes in order from one parent into the other. And we focused on two different mutation methods. One would be uniform mutation, and the other was genetic drift. So for the uniform mutation, it's very simple. We generated a random number from 0 to the length of the chromosome. And at that gene point, we simply removed that gene and replaced it with a random gene from the gene set. Now, every time this happened, we needed to check that the replacement gene would not break the knapsack limits. And this worked quite well, but it can lead to a lot of computational overhead, as often many genes won't fill that requirement. And additionally, the scope of mutation is rather low. So an additional method that could be tried to diversify your population more would be a genetic drift method, where essentially instead of swapping out a gene, you mutate the gene itself. And so the way we did that in our algorithm, each gene contains a certain number of each material, be it wood, steel, cotton, etc. And so instead of swapping out the entire gene, we randomly selected the gene, and then we randomly selected a position in the gene and cut one of the items out, be that one wood, one stone, etc. And after doing that, to three different genes, three different times each, you're ensured 100% that your chromosome will now be smaller. And then you can pull in more genes from the gene set originally and place that in that newly open spot. Now, the way that this helps is it helps diversify the gene set, which basically means that you are no longer limited to the original gene set that is randomly generated at the beginning of the algorithm boot up. In genetic algorithms, selection methods are how you choose who will be the parent to the next generation, and therefore select the path that your algorithm will take. For our algorithm, we chose to implement pure fitness, which is simply selecting the most fit member of the population and removing them from the pool of potential selections for the next generation. Fitness was very easy to determine for this problem because in the knapsack problem, fitness, you're trying to maximize value in the bag, and so fitness is simply the value in the bag, and the higher the better. For our particular project, we focused on the free lunch theorem discussed in class. Now, the free lunch theorem basically states that for genetic algorithms as a whole, you cannot say that any one method of selection, mutation, etc., will be the best, and that each problem, the correct solution, the way to the fastest convergence varies. So for our project, we wanted to compare a lot of different methods of each to figure out what would be best suited to the knapsack problem. So of the implemented methods, ordered crossover vastly outperformed everything else. Its mean convergence time was 0.04 seconds, which is twice as fast as its nearest competitor, which would be the PMX, and over 50 times faster than two-point crossover. We found that crossover in general was a much more applicable method than the actual mutation, and we're not really sure about why, to be honest. Early on, we realized that our algorithm was getting stuck at local maxima, and so in order to add more explorative functionality to the algorithm and expanding more as we went into further generations, we introduced an age limit for the chromosomes to help mitigate this issue. So we were wondering how the age affected the convergence time. And by limiting the age, as you can see in this table off to our right, the less time we allowed each parent to stay in the pool of eligible parents, the quicker it decayed. This kind of indicated to us that there's an optimal relationship between exploring, which would be letting the chromosomes die, and exploiting, which would be letting them reproduce. And for each problem, again going back to that free lunch theory, for each problem that maximum age is going to be different. Beyond just seeing the convergence time, which is the overall best estimator of efficiency of the genetic algorithm, we were interested in seeing more of the nuts and bolts of the problem, evaluating how each method finds the solutions while it evolves. So the best way for us to do that was to actually plot which chromosomes or which genes were chosen during a select generation by each of the methods. And it's interesting because initially the points are clustered towards the regions that fill the knapsack the quickest in that upper right-hand corner. And that makes sense due to the way our algorithm begins, which is to stuff the bag as full as you can, as fast as you can. And then as the chromosomes evolve, they start swapping those items out that are really heavy and big, and they start looking and exploring outside for more valuable items. And it's kind of interesting to see that exploration exploitation concept in action. Another interesting behavior that we saw is that the faster converging methods have much more dense clusters as opposed to the slower methods, which is more varied. And that's just kind of an interesting observation that we're not 100% sure how to interpret, but our goal for this project was to create a testbed for exploring the trade-offs between various genetic algorithm operators on this particular popular optimization problem. And we did this to learn more about genetic algorithms and have insight as to how different strategies and methods for genetic algorithms work and how they relate to real-world optimizations. The results from our experiment would indicate that ordered crossover performs the best in terms of finding an optimal solution in the shortest amount of time. But as we all know, that is purely for this specific application and could be very different even by simply varying the parameters of our problem. We also experimented with chromosome age and parent fitness and helping to migrate the population through that, which our data suggested that there would be an optimal trade-off between exploitation and exploration. For the future, if we were to expand this project, it would be really fun to add more attributes to the items, such as a fragility index. So, you couldn't put eggs on the bottom if you were going to be putting, I don't know, like a 5-pound weight on top of that or something like that. And also maybe having to group particular items together, because in the real world, it would make no sense to be grabbing one orange and then one granola bar and then another orange. You'd be putting together chunks of things. And so as we were to add these parameters, it would be interesting to see how little or how much our conclusions drawn here would apply to seemingly the same problem. Thank you all for listening.